a real statistician, this time Tom Nichols.
Okay, so I'll be talking about reproducibility and power, but mainly, as you'll see, power, because I think it's something that's neglected overall, but I think there's sort of a consensus that it's actually a really quite important thing. So what I'll do is I'll do a basic review of power, and then talk about the sort of practical methods that are out there for neuroimaging, and finally, why is it that we should be worried about this? So really quick review, hopefully very basic thing that everyone will be familiar with. What is powers in the statistical sense? Well, it's the probability of rejecting the null hypothesis when it is false. That is, when the alternative is true. In order to specify what power is, you have to specify what is the sample size, what is your alpha, what is your acceptable level of false positive risk, and then you also have to specify the standard deviation and the effect magnitude, which you can combine these two together to be a measure called D delta, or D, sometimes Cohen's D, which is the effect magnitude divided by the standard deviation. Fine. So this pink area there is our power. That's the probability that we're going to see something when there is actually something there to see. Just as a little practical demonstration to show you that, of course, it can happen that you have a non-zero signal, but you basically have no power. This is just a reminder that your power can never be less than your alpha, because that's where you're always starting. You're always starting with some baseline of false positives, and so as soon as you have some tiny little signal, your power will pick up from whatever that is. So here, for a tiny little signal, we get a power of 5%. Then for a sort of greater signal, if we had bold percent, a change of 0.2, and that with this sort of standard deviation up here, this grows and grows and grows. But the main thing is, and honestly, as a statistician, why I've tried to do as little with power as possible, especially when people come to my office asking for it, is that this is all fiction. It all depends that these are the right numbers, that this is the exact right standard deviation of the bold response in the population, that this is the bold response that you're going to observe. If I already knew the bold response, why would I be doing my experiment? Is the typical question that you have. So why are we doing this? Well, I'll get to that in a bit. But the other thing that we have to grapple with in the setting of imaging is multiple testing. So let's say we have 100,000 tests in a 100,000 voxel brain. How do we deal with this? Well, in some ways, the easy part is setting the alpha. You have to set what is going to be your criterion, and so we have to adjust this. We have to make this higher to deal with the fact we're dealing with lots of tests. For example, I could use random field theory. I could reasonably say I'm going to use a standard M&I mask, and I'm going to have a full tab maximum of 8 millimeter smoothness. That gives me 3,301 resols, and then that tells me that I need to use a threshold of 4.93 if I have lots of degrees of freedom, and that's this alpha here. Okay, fine. So that's one of the parameters that I have to feed into my alpha. What's the other one? Well, the other one is, what is the effect magnitude? What is that response? And of course, now I don't just have one, I have 100,000. So there's basically a huge, lots of configurations I would just try to illustrate in the cartoons. Do I have just one voxel here, one in that one there? Was there 3 there? Was a whole region, left, right, bilateral? There are a whole span of possible alternatives that could be in place and could be giving rise to a signal that we want to observe. And of course, oh yeah, by the way, we have to specify the standard deviation as well. So this is why power is very difficult in imaging, because we have to specify all these things. So now what I'm going to do is going to march through what I think are kind of 4 practical ways that you can do a power analysis. The first one is what I've basically recommended for people sort of since I've started, as a faculty member. Usually when it's someone coming to my office, like, the day or 2 before a grant is due and they need some sort of number because they know they can't get a grant unless there's a power analysis in it. But I can now dress that up in fancier terms because I've worked in the drug industry. This is the clinical trials approach based on a primary outcome. So you say, instead of searching the whole brain, you say, my study is all about average bold in the amygdala. And my study will be a failure if I don't find something there, and it will be a success if I do. And so now I need to and so you're basically saying that regardless of what I do, actually the main thing in my study is a univariate scalar outcome that you will compute from imaging data. And so what I will need to compute my outcome, which is the standard, the bold response in this measure and its standard deviation. Now, to be clear, this is you have to think like you're doing a registered clinical trial, and they don't do imaging. They depend on somebody giving a statistician an Excel spreadsheet. So you have to reduce the data to one number per person. So in this case, you'd be applying this mask to some previous data that you have in hand or that has been thoroughly reported in some journal. And so then you compute the mean across subjects and the standard deviation. There you go. You have, now with that, you have a mean, you have a standard deviation, set your alpha, and you know how many, and then you can do a power analysis and see how many subjects you need to get to your desired 80% power. Again, the alpha, you could use an uncorrected approach, or you could try to now extend this and based on this say, well, okay, I could say this is the response at one single voxel, and I'm now going to consider searching over the voxels in this region or a larger region, and so you could use a more stringent alpha based on that. But I just want to stress that it's a rather simplistic approach because you're not really accounting for the fact that if you do a voxel-wise approach, it's not just one voxel that's showing this response. So should it be more than one? So it will probably be a conservative approach to power. Okay, and also I can recommend if you've never used G-Power as a freely available package for power analysis for basic things like this, and it's pretty handy. Okay, so the limitations. It's not very flexible. For one thing, aside from that you need to have the data generally to come up with these estimates, this power analysis is only relevant for this particular design, this particular experiment with this sort of run length on this scanner with this sort of data quality. It doesn't generalize in any way. And so, for example, if you wanted to say, actually, no, I don't have time, I need to shorten my run length by 50%, well, this isn't going to help you predict what that modification is going to be. Or if you wanted to change your event-related design to add another event type or change the random spacing, this is not going to help you predict what the power would be under that modification relative to your pilot data. And of course, it doesn't account for the spatial statistics. Again, you can change the alpha, but it's not going to, for example, give you a way to predict what your cluster size power would be. Okay, so the next more sophisticated approach you could take would be to do something which I'll call mixed effects fMRI modeling for power. So if you're really going to consider a group analysis with both within and between subject variability, so not only do you need your effect size D or delta, you need to then get a handle on the between subject as well as the within subject and the between subject variability. So what I've illustrated here is a second level model that we generally fit in something like SPM or FSL in the OLS mode, where each observation that we have is a contrast. And so it's each subject has a contrast image, and we model that in a regression. Here I might be comparing males and females or young and elderly. But actually, so usually we fit this happily in ordinary least squares, but the actual true state of things is that the covariance is actually rather complicated. The covariance has a the variance of the error has a within subject component and a between subject component. So what are all the pieces here? Well, there is the component that has to do with the intra-subject correlation, how temporally autocorrelated is each subject. There is the intra-subject's first level variance, where this is a good subject, do they move around, was the scanner behaving that day? And then this measure, which is you basically need to use iterative methods to get a good estimate of that's the between subject variance, as well as all these things here. So you have to specify more, but then this gives you the flexibility, because then you could consider different designs, different XKs, shorter runs, longer runs. In the effect of sort of higher autocorrelation. And so with this, this is work I did with my former student, Jeanette Mumford. You can then play games like, well, how long do I need to scan someone? Can I consider using varying durations of scanning time? So here we looked at the scanning time in hours versus the power that you get for a given number of subjects. So of course, for each number of subjects, your power goes up. But we put a cap on the total number of scanner time that we had a budget for. And so you can see that even so, say with 12 subjects, you can scan them for a long time, but you're never going to get up to that power whereas with 24 subjects, you could scan each of them for a shorter time. So this is something that you could not do with the clinical trials sort of single outcome approach to power. Jeanette has implemented this in a toolbox. You can get to it from there. It's got tools to work with FSL and SPM design so it can read up your existing designs, because that's the main weakness of this approach, is that you have to define all these other things. And of course, I don't think any of us have intuition on what is the auto-regressive coefficient that is common in our data. And we don't have an intuition on that, but then the toolbox will go and it will extract that from pilot data that you have. Okay, so the next method I want to talk about is one that tries to account for the spatial statistics, because the previous ones are while they're doing varying degrees of trying to estimate what is the structure of the data, either between or within subject, but they're not really doing anything sophisticated in space. However, one of the most popular methods for assessing statistic images is cluster-wise inference. So we like this because cluster-wise inference generally gives us greater sensitivity. I do have to mention a paper from Tor Wager's group, which pointed out some of the pitfalls to this. That greater sensitivity can come from a lack of spatial specificity with bleeding of regions. But interesting read, I recommend. But still, it's a cluster-size inference is used a lot. So could we get inference? Could we get a power analysis for cluster-size inference? And another former student of mine, Satoru Hasaka, developed work for cluster-size inference power using non-central random fields. It does require that you have to specify the shape of the activation that you anticipate, and then it will use results from random field theory to say what is the probability of observing clusters above a certain size. Now, you don't have to specify this. You can't. Oops, sorry. You don't have to specify this map. You can also get mapped to local power, and that's what he's showing here. And these are basically maps of saying, what is my chance of observing a cluster of a given size here? So basically, he considers alternatives of a locally, it's like a spotlight of signal moving around. The other thing here he does, just for comparison, is that if this is the power based on the single outcome clinical trials approach here, compared to power based on a non-central random field. Now, of course, what you notice here is that the power is substantially lower, and that is the trade-off of, because this is actually doing a whole brain inference and saying what's the chance of seeing a given signal, a cluster-wise significance based on a signal in this particular region, whereas this is when you commit to only looking in that region and doing a scalar outcome. So this is, there's no, by searching over the brain, there's no free lunch. This is the adhering to Jack's principle, and this is quantifying the lunch you are losing, that you have to pay for. And finally, I want to talk about some recent work that Jukka Dyrnes has been doing. Because the one thing that both those methods still have is that they're still relatively difficult to specify. In the previous version, you ideally would specify the exact shape and location of your signal. And so working with Jukka, we've been trying to figure out simpler ways, and something that seems to be a really simple approach is to work just with peaks. So peak inference is something you may not be familiar with, but it is done in SPM, actually ever since SPM 8, and it makes inference on the local maxima above some threshold. So you specify some arbitrary threshold. Normally we think of it as a cluster size threshold, but it also gets used as kind of a screening threshold, so we ignore any local maxima below this threshold, and then we just consider the local maxima above that threshold. And then we make inference on which of these are significant or not, here indicated by this sort of threshold here, just declaring significance or not. So ever since SPM 8, there actually has been the ability to get uncorrected p-values for these, and that's the basis of SPM's FDR significance on peaks. But this also gave us the way to make inference on these individually and to do power analysis. So we can do a power analysis based solely on the mean peak height and the size of the activated region. So that can be expressed as a volume or just a proportion of the search region of the mask size. And of course, it is using random field results, so we do need to know the full at maximum smoothness. But based on that, you can get power curves, and you can get that for FDR inference or uncorrected or family-wise error. And again, there are these two parameters that do need to be set. And again, it's not something you can necessarily would have intuition on, but Yucca developed methods to estimate those key parameters, the proportion of the peaks that are not null, and then figuring out what their mean intensity is. And Yucca also has a poster here describing this, and this is the link to her NeuroPower app that will do this. You can load up T images to this, and then it will allow you to make a power maps like this. Okay, so just reviewing these four, so the clinical trials outcome is easy but not flexible. It doesn't really reflect the image-wise nature of what we're doing. The mixed effects power has the most flexibility and really allows you to explore a whole bunch of different things, including optimizing experimental designs in terms of event-related trials, arrangement, and et cetera. The random field theory cluster is unique in using the cluster size, and then the peak power, I think, is easy to use. But then I just step back again. So why are we doing this? Why do we really care about power? Well, this is the big reason why we care about power, and this is a concern about replicability. So again, you might say, I got a significant result on my paper, on my results, so why should I care whether there was high power or not? And this is why. It's the law of small numbers. It's also known as the winner's curse. Off here is a box from a non-imaging experiment. This is actually not, it's 256 experiments. It's 256 meta-analyses for a binary effect. This is the Cochrane database. The Cochrane database is a collection of meta-analyses for clinical trials. And the observation here is quite clear that basically as the sample size goes down, the estimated effect size, in this case it's an odds ratio, goes up, which is a bit troubling. And so the reason here is that, well, what are the features of a low-end study? Well, with low-end, we know power is going down. So if you get a significant result, the only way you're going to get a significant result is if you have either a randomly high effect or randomly low estimated standard error, randomly low variance. So basically, this low power is if you go in, if you observe a study that gave you this result up here, you might be going and saying, I'm going to go replicate that study, and you're going to have a hard time because that was a rare study. There were probably lots that weren't there. But actually, let me just go over the two other sort of more nefarious reasons that might give rise to this pattern. And that's suppressed studies and biased effects. So the suppressed studies are the ones down here. So those are, I guess it's not nefarious. This is what's known as the file drawer problem, and those are the studies that were started, commenced, and they're negative, and then we don't see them. They're gone. Or they were submitted and they're rejected by the journal. The rather more nefarious one is what's known as vibration effects, where those studies were completed and then they didn't get the results they were hoping for, and so then they tried something. So let's go through each of these in turn. Well, actually, there's nothing more to say about the file drawer effect, but I just want to do a little self-promotion that my student and I have been working on methods to estimate the fraction of these missing studies, estimating the number of file drawer studies, and we are doing that with the distribution of the number of foci in meta-analysis databases, because, of course, meta-analysis databases do not have papers in them that have no foci. They only have positive papers in them. And so there's this sort of an absence of zero counts, and we can use sort of basically the laws of how statistical counts behave to estimate what is this zero count. And come to the poster to see all the details, but what we're getting at is we're looking at something, we seem to be finding that about 1 in 10 studies are missing. So for every 10 studies published, there's at least one out there that's been suppressed in some way. What are vibration effects? Well, this, I think, once I explain it, everyone should be familiar with is, when people get a negative result, they might say, well, actually, maybe I have some subjects with bad movements, or maybe I should try that global signal regressor. Some people like that. Well, actually, no, maybe I really was interested in the frontal lobe, so that's where, that didn't work. Well, I think it was the DLPFC left, right? That's what the literature said. I saw that paper once, right? And then, actually, I'll look for XYZ coordinates that are near my activation. I know I've seen that in that other paper, and then you put it, and then, and surely that will work. So these are vibration effects, an adaptive modification of your analysis protocol to your data. That's what it's the vibration. It's the shaking the box until you see the thing you want. And so these things are only going to lead to inflated false positives because you don't reanalyze your data until the result goes away. Although, I mean, some people, we all should be very critical about our results. We should try to analyze it and be sort of the best critic. So basically, in brain imaging, as well as other modern scientific methods, there's a huge number of pre-processing steps, analysis choices, and it's really important to even you don't have to be sort of an evil scientist to fall prey to this. And the best thing I can recommend is to make sure that your lab sort of basically has established ways of doing things, established protocols, write them down, and so that you're not sort of left to sort of fish among all the different ways you can do things. And then the other thing that I found to be really sobering, this is a result from Button et al. From Marcus Monafo's group. This was a kind of acute meta-analysis of meta-analyses. So it is in neuroscience, but non-imaging neuroscience. And so they used, in each meta-analysis, they used the average effect size of each meta-analysis to define what truth was. And of course, once each study, when it's published, you don't know what the truth is, and so you cannot really do a power analysis. But retrospectively, after someone many years later has done a power analysis, you could use that power analysis, when someone's done a meta-analysis, you can use that later meta-analysis to go back and infer what would be the power for that study. And so for all the studies that went into all of the meta-analyses, they can now work out what is the power. And they computed that the median power among all these studies was 21%. So that's quite sobering. So that's saying, what does that mean? So median. So that means 50% of all neuroscience studies have at most a 1 in 5 chance of replicating. That's what 20%. So the median is, because we're talking about the median, and a power of 20%. What does that mean? That means I have a 1 in 5 chance of getting a positive result. So if all those studies were truly having, and that's also, we're not even counting the false positive studies. So we assume that they're all really true studies that are all ready to be replicated. It's saying that about more than half have less than a 1 in 5 chance of replicating. And that's sobering, and that's why it's worth sort of having an eye on what the power of your study is. So their recommendations were sort of do power calculations, disclose methods and findings transparently. One thing you can do is you actually can pre-register your study and protocol and analysis plan. This is sort of, I don't know if it's controversial, but it's not very many people are doing it, but there are some pre-registered mechanisms. I think it's cerebral cortex that allows you to do that. Make your study materials and as much of your data online as possible. I will readily admit that sort of making your data ready to be shared is an exercise and can be difficult, but the NeuroVault is a project to simply collect the Z images. It is not really difficult to go and click and upload your Z images, answer a few questions about your study. It's really an easy thing. Thanks. And the other thing you can do is to do things like Enigma, and basically to join collaborations that basically extend your sample size and increase your power and give you a better chance of replicating findings. All right, so I'll stop here. The end of the story is, after I showed you all those different tools for power, is that the reason you should care about it is that because power equals replicability. Basically, your best gauge of whether your result is going to be replicable is based on the power of that result. I've talked about primary outcomes. This is a good, simple way, really, to just appease reviewers, but doesn't really reflect the sort of the complexities of how we analyze our data. And thus, I'd sort of recommend you to try out one of the other methods that are I talked about. And I'll stop there.
Okay, we can take a question before we have our break.
Just a comment on the, is that working? Yeah. A comment on the probability of replication from the Button paper. I think what you meant is that it's it's not the probability of replication, it's a probability, this was just a power. So if you want the probability of replication, you need to have the probability of the H1, the prior probability of H1. And that's not exactly
In
the
his,
same.
yeah, I was
So,
assuming, I was giving them the benefit of the doubt that every one of those studies was a positive study, but you're right, if you actually are not so generous and say that actually,
That's actually a fairly different number in many
Yeah.
cases because you know it depends on if your H1 hypothesis is likely or not. Very
the
much.
meeting hasn't even started, JB, I didn't want to really make everyone cry. That it's,
That's an
a
important
good
point
point.
because this crowd should understand that aspect that if you really need to know how likely is your hypothesis. If you have a very unlikely hypothesis, then you really need to have a way much more greater power to get a good replication probability. And that's something which is important to point.
that's a great point.
Thank you.